那我不在的时候，这个位置谁坐？我要认识这个弟兄，然后没有问题，他在什么？跟他认识一下。听说了一个学期了。上次是不是发一个 PCA 的让给我钱？给他买一点小品。
没有啊，没有传到。
上面有网友吗？应该是有的吧。园长。我周三，我就周三，每个周一都有。周一是让名字是对呀，周一我一不想来嘛，来跟没来。
All right, we'll go ahead and Get started. So welcome to the 24th session of EE 7391. One of the things I thought I would do today is talk a bit more about convolutional neural networks, because I think it's important that you understand kind of the issue behind the sampling process, which is really sort of the decimation piece associated with computing the gradient of cost function. I think that's really the thing that tends to hang people up when they're looking at these sorts of problems. And so what I thought I'd do is I have a MATLAB session open. I'm going to actually type some things in MATLAB. Now, whatever I type, I'm going to save, so you don't need to necessarily write that down. But at the same time, I'm not typing the solution to problem 4 of the current homework. So there's additional things that you'll end up having to do and modifications you'll make. But it'll illustrate one of the issues that you have, and actually one of the connections that we have between neural networks and adaptive filters, particularly in this convolutional space. And it has to do with something we might have briefly talked about. I don't think we've gone into depth. But that is in Chapter 8, Frequency Domain and Lattice Adaptive Filters. There's actually this result, which kind of is interesting. You know, we talked about this kind of update. Well, this update should look familiar. It's actually the update that we use for neural networks where, you know, we have patterns associated with this. But in this case, the data is actually a convolution, as opposed to, in other words, these are actually vectors that are shifting in time. And if you will, we're not updating, you know, every n, if you will, samples. We change this to k and this to k plus 1. And so we're iterating on a different schedule. But the important thing to recognize is that, in fact, when you look at kind of the gradient of the cost with respect to the weights, you get an error times the data, which is convolved. So this is actually a convolution for a computation. And you can use convolution to do it. So it actually means that when you implement convolutional neural networks, you use convolution twice. You use it once to actually compute the output. And then you use it a second time to actually compute the updates for the parameters. And so it shows up in two different places. But I'm going to make that actually even more clear by actually doing this within code, and we're going to construct some code that looks like adaptive filtering code, but very quickly you'll see how it relates to neural networks. So in this case, I'm going to choose a signal length of 1,000 samples, and I'm going to have maybe 20 patterns. So this is kind of the notation of the class that we're using for the neural network side. And then I need some number of iterations for the algorithm. I'll say that's 400. This is just saying I'm running 400 times, 400 epochs, if you will, through the training. And then I need some data. So I'm just going to generate, for this toy example, some random Gaussian data, which is L1 long. So that's the pattern length. And then N is the number of patterns I have. And then from that, I need to generate a D. Basically, what I'm going to do here is generate a desired signal. But the way I'm going to do that is I'm going to do kind of what we've done in adaptive filters, which is to generate some random coefficients of, we'll make them rand-n as well. So kind of random coefficients for W-opt, and we'll make B-opt. This actually I want to have positive, so I'll make that rand1 times 2, as it turns out. And then I'm going to say for n from 1 to n, I'm going to generate my D, which is basically going to be the convolution of x with W-opt. You have to excuse me, I'm being a little under the weather. But in this case, I only want valid outputs. Now, if you look at what the convolutional operation does, and you're allowed to use conv in your code, it's fine. What this does is it actually produces the convolution of the W-opt coefficients with x, but only over valid points. So this will generate a sequence which is basically the length of x minus the length of W-opt plus 1. That's the number of valid operations or valid outputs that you get when you do a convolution. And then, of course, I have an offset, which is B-opt. That's my offset for my signal. And that's going to be the case for every pattern. So basically what I'm assuming is that every pattern is going to have an optimum coefficients W opt and then an optimum offset B opt. And then we'll end that out. Now, in order to kind of make this look more like the neural network problem, I'm going to do one more thing, which is I'm going to say y is equal to d dot star d greater than 0. And this is effectively like saying y is the max of d and 0. But I can't do that very easily with kind of scalars. I'd have to go through every scalar and do it. So it's a little tricky to do that in the context of MATLAB coding. So this is actually a slightly better way to do it over here on the left that'll actually ensure that that's the case. So basically we'll retain all signals that are positive. Now that's basically my data setup. So I have my training data Y, I have my training data X. These are my input patterns, these are my output patterns. And I want to build a system that will estimate the W opt. Well, I can do that. And the way I'm going to do it is I'm going to go ahead and generate a for loop, which is going to be 1 through the number of epochs I'm going to train for. Now, in order to do this, I need to compute a gradient. So I'm going to have a gradient that I'm going to have here, which is grad J, which is going to be zeros, length L. Actually, I haven't chosen L yet. I'll go ahead and choose L up here to be 10. I just need a number for my model. So this will give me my model length, and then this will give me my gradient length. But in this case, I'm going to say L plus 1. This will basically store my gradient for the kth iteration. So I'm computing the gradient across all patterns, that is across all ends, and across all shifts vertically, because I need to apply a filter to the vertical dimension, if you will, to produce my output. Now, at this point, I'm going to do what I do in adaptive filters, which is to go sample by sample. So I'm actually going to step through this. So I'm going to say capital X is zeros L1. I'm going to say this is basically setting up a shift input vector. So I can step through this. For I from 1 to L1, I'm going to take my buffer. Think of this thing as like a L sample buffer. Then I'm going to say x of LL plus 1 gets x of LL, and then the first element is going to be xi. And then at this point, I can now compute outputs. But I can do this for basically I greater than equal to L. So I'm going to constrain myself to basically only have valid input. So this is going to ensure that my buffer fills up with data. Once it hits L samples, then this thing is now full. It has all valid points. Oh yeah, and I realize now I need to specify up here also probably a D hat. D hat zeros, L1 minus L plus 1, 1. So I just need a D hat as a temporary thing. And what this is going to do is it's going to say D hat, oh, and that's right, and I need J, I need my J, so I'll say J is equal to, I plus L minus 1. So that'll make my first element 1. D hat J is W transpose times X plus B. That's my single sample output. Y hat will be max of D hat J and 0. Here I can do it. That's going to do my ReLU operation. And then I have an error, EJ, and I guess I should probably specify an EJ up here too. L1 minus L plus 1, 1. So now my EJ is going to be, in this case, Y hat J minus, actually, YJ minus Y hat J. And then my gradient I'm going to accumulate is going to be gradient plus EJ times And here I'm going to say x and 1. So if I append 1 to x, I'll get both my data and my bias term. Bias term has like a multiply of 1 on it. So this allows me to accumulate my gradient here. Now, this is fine if the output's always non-zero, but remember, I've also got the condition that my output has to be positive. So I have to say if d hat j is greater than 0, then I do the update. That's the only time I accumulate. Otherwise, I don't. Right? This is basically the result of when you're doing a computation of a gradient. The ReLU operation only allows an output when the linear part going into the ReLU is greater than 0. So this means that the gradient is only computed when the linear part of the signal is greater than 0. So that's when we accumulate the E times the X. And that steps through now all samples in the current pattern, right? That's what this does. And then this will actually do it for all, let's see, for I from 1 to L. If I is there, that's good. If that's true, that's good. And then I want as well, that's that. Oh, xi, there it is. That's my issue. I need to have, yes, I need to have xin, right? Because I have each pattern. And so that means actually here, I'm going to have these calculations, but it's going to be for n from 1 to capital N, right? So I have that, and then my gradient, actually my gradient has to live outside of that. But I'm stepping through all my patterns for n from 1 to capital N. And then I have my d hat and e. I'm zeroing that out. I feed in the new data. There's that. Here I have yjn as being that, right? Yep, because that's my y up there. So for the nth pattern, and then y hat j is just the current output because it's depending upon xin. So that'll produce the resulting gradient. So now, if I look at all this, I think I need to indent this guy just to make it nicer. Indent. There we go. All right. So now this is going through, and then this one is end. Now I've stepped through all my data. I've computed my gradient across all my data. So this is accumulating all the gradients that are valid. And then finally, I need to do my updates. What do my updates look like? Well, they look like W gets W plus some eta. Now here's the thing. I'm going to divide by both L1 and N, the product of L1 and N. Why? Well, I can kind of think, I'm stepping through L1 times. And I have N1 input patterns. So I really have kind of L1 times N different things that I'm potentially averaging together. Now, some of these will be 0, but that is the rough value that I need to scale by so that, basically all my gradients are being sort of properly averaged. And I multiply that by the gradient of J, 1 to L. So I have that. And then B is equal to B plus eta, again, divided by L1 times N times gradient J1. Sorry, L plus 1. And this will now produce an output which should converge to my W opt. So let me look at this. W and W opt. Actually, let me do this. W and B. W opt and B opt. So if I have everything properly working here, this guy should allow me to generate some data. And then as it steps through, it'll then compute the updates for W, and W should converge to W opt. But I'll put a pause in here. I think I pause. I don't think I need to pause it by much. I just need to pause it so that it'll actually stop there, show me something. past versions of MATLAB required this. It may not need it anymore. All right. The only thing I don't have is eta. So eta 0.1, pick a value for now. We'll copy this over. Yes.
The gradient J is and the below is gradient L, so it won't work.
So I have gradient J from 1 to L. W is there. I have, oh, yeah. Thank you very much. Actually, this is L1. This is L1. That's L. Up here, I have L plus 1. So, yeah, let me just see. And then, oh, yeah, I see what you mean. I have gradient J and gradient L. That's the naming convention. Thank you. Thank you very much. Gradient J is there. I define. I accumulate, and then use gradient J. Okay, good. So let's go ahead and try this. Unexpected. Why is it not liking that? Interesting, because I didn't have any problem with that before. All I want to do is test it for I greater than equal. For I greater than or equal to L. Well, we'll just do I greater than L minus 1. But why is it not? Should allow me to do that. Control A. No, it doesn't like that. Oh, sorry, no, 4, I need if. Yeah, I need if, thank you. Yeah. If, there we go. Now it's fine. Correct. All right. Oop, but I have my W. So let's make sure I initialize. Oh, yes, I didn't initialize my W as well. I have to put my W up here, too. W is 0.01 times rand n. L1. B, I need to initialize. We'll initialize that to 0. So now I think I have my initial values, which should allow me to go. Let me do some things here so that you're not hurting your ears anymore on the video. Thank you. I can tell when there's an error. And it didn't like something, and I wonder why. I think everything should be okay. Let me go ahead and just check things here. We'll go ahead and run this guy, because that works fine. And that works fine. And that's fine. I'm just checking through. See if I have any other coding issues. I greater than, that's that. That's that. That's fine. And that should be fine. And then this. Grad J is getting defined, so it's getting accumulated. And that's being there. And we're having that and grad J. Let's take a look at I. Well, we are getting to the length. I'm wondering if it's the issue of the fact I'm going all the way to L minus 1 is the issue. That might be the problem with this. Although I don't think there should be a problem with that. That seems to be the issue. Because I'm able to get all the way to 983 with this, and my n is 1. Or sorry, my n is 20. So I'm actually able to get from I and n. That's interesting. All the way through. So that should be fine. Unless I mistyped something, but I don't think I have. Because that's D hat and E. Sorry, I'm just checking things here just to make sure. Let's go ahead and get rid of that for now. My W did update. My B did update. Oh, actually, my B did not update. So I think some issue is happening prior to that. All right, let's do this again. And it doesn't tell me where that particular problem is. So again, I'm working from a version of code. Should be okay. Oh, it's Y hat. There's my Y. Well, that might be part of it because I have YJN there and I have Y being over here. I have that. And I have J. Oh, that may be the issue. J is, if I is 983, J is 992. Ah, yes, that's my problem. Silly plus 1. There we go. Yeah, in other words, when this is greater, when this is L, that should be 1, and that's the problem. That's why I didn't like it. So I had a typo there. All right, so now it's functioning at least. Now I need to go back and do this. W, B, W opt, B opt. Start tracking this. All right, so my hope is that this actually converges to the rough value that I'm seeing there. Looks like it is actually, right? These values are actually going towards the values that are here, right? This guy's going down, that's close to that. As it goes down, starts to slow down. Yep, looks like it's converging, right? So this is showing us our estimates, and this is showing us the values after 400. Okay, I got pretty close. That's pretty close, pretty close. I'd have to run it longer. But clearly, my values here are converging to those. Okay, good. So now I have a functioning algorithm, which is what I wanted. Now what I want to do is kind of speed this up, because this overall algorithm is fine in terms of a gradient calculation, but the problem is I'm doing all the stepping, right? I'm stepping through number of patterns, which is fine, but then I'm actually stepping through all the shifts, right? I'm doing the convolution. So I want to do something in place of that, in place of that calculation. Well, I'm going to do an alternate calculation. I'm going to actually do this gradient calculation another way. Rather than doing all the step through this calculation, this is what I'm going to do. I'm instead down here, this is again outside of that whole loop involving I. It does involve n though. I have to do the calculation within n. So here, I have to do the calculation within n. I'm going to now compute d hat c, which is like the output, which is the convolution of x with w valid plus b. So now, rather than stepping through and shifting the vectors, I'm going to use a convolution operation to compute the output. Then my y hat c is going to be, in this case, I have to do something kind of interesting. Max, and here I'm going to say d hat c transpose, because remember, this d hat here is a column vector. So I make it a row vector, and then I put some zeros below it. And that will basically, when you do the max operation, it does it on columns. So this will do the maximum of this and the zeros, and then yield the resulting output. And then, of course, it's the wrong dimension. I gotta flip it back to columns again. So this takes the data and turns it into row samples, and then I can do the maximization and then shift it back to columns again. Then I'm going to compute my error as being basically dn, actually yn minus y hat c, right? I have that. But I'm going to do something else. I'm then going to multiply it by, in this case, d hat c greater than 0. This does basically that ReLU operation in terms of the allowing the gradient to only happen when the linear output's greater than 0. And then, now that I have this, I can compute the gradient in the same way. I can say gradient gets gradient JC plus, now here's the thing, conv, and now the thing is, when you do the convolution, this is actually shown here, when you do this convolution for the updates, these actually end up being correlations. In other words, the errors have to actually be reversed in time. And I know it's not necessarily obvious that that's what's happening, but it is. It is a correlation that you're doing with your data, not a convolution. And because of that, we actually need to deal with that correlation. By the way, that actually happens in the algorithm because there's a conjugate when you're doing products of frequency operations. You need that conjugate to do the time reversal. But it does mean we have a time reversal here with respect to the computations. And because of that, because we're doing correlation instead of convolution, then what we need to do is we need to take x of n minus 1, 1. So sort of take, for the current pattern, time reverse the data. But I convolve it with EC and I take the valid part, and that will actually yield a vector which is the right length L. Because the valid part of this long convolution with a slightly less long convolution is something that's length L. That's kind of the neat part of that. And then for the bias, I just take some of the errors. And that's my resulting update. So notice I have replaced kind of all this sample by sample stuff with basically 4 lines, which is doing the output computation, the max ReLU max operation. Then it computes the error. And by the way, this is obviously going to change in your code because you're going to do backprop, right? You're going to actually compute another layer's forward output and then do backprop to produce errors here. But once you produce those errors, you're going to multiply them by this and then do this convolution operation like I'm showing you here. Okay, now that I'm doing that, I'm now, actually I'll change these over to that to see if those work. But what I should also do is I should check grad J and grad JC and see if they're actually, you know, the right size, or sorry, they actually look like each other. And in fact, I'll even subtract them. So I'll subtract them. So now I'm gonna spit out some outputs, and here I'm actually gonna pause it because I want to see what happens here. So now I've got 2 versions of the code running at the same time. They both should do the same thing. So we'll go ahead and run this, see what it does. Oh, it doesn't like my definitions. I might have some small typos in here. That should be 1 there. Okay. Okay. Well, one thing I can see is I think I've got the same computations because this is, you know, this first column is the gradient in the old way. The second column is the gradient using the new way, and the difference is a bunch of zeros. Now I know you're saying, well, how do I know those are zeros? Well, actually they are zeros, as it turns out. They will end up being zeros. In fact, actually, there's something else I want to do. Now I realize. I want to divide those. Let me divide all these guys. Let me normalize them all by L1 times n. So now they're the same size, sort of overall. So now I can start seeing some other things. So yeah, so now I can clearly see every once in a while actually I get a pure 0 in my difference, which means numerically. These are on the order of 10 to the minus 17 as it turns out. And then these are the weights. So we'll go ahead and let this run now. And we won't pause it that often. Do this. So now I'll run this guy. And now this should actually converge. So again, these are the same. These are the weights that are converging in this 4th column. The 5th column are the optimum weights. And I can see 4th column is moving to the 5th column. First 2 are essentially identical, and the difference is 0. And actually what you see is as you get closer, the gradients get smaller, right? Which is what you'd expect to happen. So as this thing converges, then these gradients get smaller and so on. So this is showing that this all works, okay? All right. Now, again, all I'm really showing you is that, yeah, we can take something that looks like an adaptive filter and implement it either in sample by sample form or kind of in block form where I'm averaging across, you know, not just, you know, running the filter through the patterns, but actually averaging, summing across multiple input patterns too, summing across n. Where it gets very interesting is what about, not dropout, but what about pooling? Pooling involves selecting samples at the output, right? Well, in our case, what we're doing for the homework, it's stride convolution. So you're doing, I think it's every other sample. That's very easy to deal with from the standpoint, I mean, we could do it with respect to the outputs. Maybe that's the easiest way to do it, is just to say, all right, if J, rem J0, sorry, rem J, actually I'll follow the same code that I have. If rem J 2 equals 0, that's only then will I actually compute an output, do an update, right? D hat, Y hat will be out, you know, and so on. So basically what I'm doing now is I'm restricting my outputs to only times when I have even samples. So this is the stride convolution, right? And it's producing outputs. Now, granted, it is producing outputs with zeros in between them, right? I mean, it's only giving me a D hat J every even sample, and every odd sample will be 0. That turns out to be important for me for my calculations. But for my gradients, it's clear that this needs to be true, and I need to have an even sample, and I need to have this condition for my gradient to accumulate. Okay, that's a pretty straightforward thing. How does that change things down here? Well, it changes it in the following way. What we need to do is we need to think about this. We actually need to compute this every other sample. So one way to do that would be, rather than doing this, I'll just comment it out. We'll say EC is zeros, L1 minus L plus 1. I need to keep it the same size. And then every other sample will be 2, 2, length, EC. So I'll do every other sample. And then ECNS will get this guy. We'll get those samples. So this will be Y and S, Y hat C. I take that every NS, and then D hat C and S. So now I'm only doing the error computation every other sample. But notice I need to have a vector which is not every other sample long, but every sample long, right? In order for the convolutions to work out, I need to have this be this length, because otherwise I don't get the right gradients getting computed. So I have to have that vector. Basically what I need is I need to have an error vector where every other value is 0. Because that will give me the resulting convolution size I need to be able to make this valid computation, and so on. So that's the change that enables us to actually deal with the sampling. So we have every other sample, because we're only producing outputs every other sample. We might have non-zero out or 0 outputs when this is not true. So we have those things happening. Okay. Otherwise, this code should run the same way. So we're going to go ahead and try this. Let's see what happens. Well, clearly the gradients are the same. So the math in the block version did the same thing as the math over here. And every other sample still works, right? This guy is converging to here being roughly that, and this guy is roughly that. So this is converging down. It's slower, by the way. Why is it slower? Because there's fewer training samples, right? If you with the outputs being what they are, there's actually fewer when you decimate. You have fewer data that's actually being used to sample. I guess I could up my eta, make that maybe 0.2 to make it run faster, although now I'm changing my data fully. But that's also another thing that's happening, is that I might want to increase my step size because I have fewer samples. But you can see this does converge and produce a proper estimate. So everyone see what we did there? It's important to recognize that when you're doing the computations, you need to consider, the subsampling process, taking every other sample in the stride convolution, and then doing the resulting update. Now, if you had, instead of subsampling, a max pooling operation, that would simply change what this vector would do. This vector would now be data dependent depending upon where the x's were in the max operations that you did for the outputs, for max pooling. Okay, so that's the only thing that would change here. But otherwise, the same operations would hold. So you could use the same idea with an NS vector, which would be signal dependent now. Signal and weight dependent, actually, to figure out basically what values to keep in your error when you do your updates. Otherwise, that would work as well. Okay? Any questions on this? Like I said, I wanted to show you this overall process because I think, that when you're looking through the convolutional neural network literature, it's not clear how sampling is being done. It is the case that you have sort of complicated sampling operations going on. You've got situations where outputs are only non-zero when things are positive. You've got situations where you're taking every other sample. Or you might have a situation where you're taking samples that are, the maximum of a region. Those are all basically sampling operations. The basic code is the same. You do a convolution operation to produce outputs, and then when you compute the gradients, it involves another convolution operation. And that's what this shows. For every layer, that is, that you're doing it. All right, I think this is actually a good point to pause, so we'll go ahead and pause here, take about a 5-minute break, and we'll come back at 5:45.
这个是 Grad JC 是他之后做康顿之后，这个原因是这样写 ，Grad JC 应该是为什么不是永远有问？我一接着一进公司。因为你这儿是零是吧？不应该是这个是应该是一选这个这个相当于是那月性的 Y 是计算生成的 ，Y 是计算生成的 ，Y 是公式。对，然后 Y 那你看你的 WiFi 的是吧？是把它这个估计也是按不对。啊，怎样？我看你 WiFi 我估计都有。不是，是这个应该是不对。但是你看这个就是 prediction 的这个它是 converge， 那个 B 是对，没有，这是 W， 这个是 W， 这两个是 W， 这个是 Grad JC，Grad JC， 就是它把它放一起。哦，这是两个语言的一个。在它下一个这儿，都一样的，它是在 random， 然后 L 个，对。他们其实能考为什么？看他这个可以看漏了。他就是这个上网做什么？对啊，我不知道为什么。切换好久。这个是。有合作伙伴的，下一个公司好了，下次我看我有人没有啊，不是，他就是要我写个社交，他要别的啊，我靠，做了，那我做了，对呀，你写个你看你不是可以看3吗？哦，你这个3在4，这个这应该是可以的，他说李老师说到时候可能会让我写个接口，写成那第2个 Python 的接口，我意思是就是一下需要然后他一天给我看一个，但是你俩干的这种，我俩就是合作要发动很好，我没意思，没有，基本上你把这个一打完。
这个拼销母的形成的条件，就是之前提出的这个前端得形成了。它这个它这个就是几条线，
然后评估过，本来它应该是这样的。如果这个新进出来，它在这里就是保密的，所以就是它的结构就是这一点，这是 N 派的。
我知道你的说他们这边本来是放给这个，但他们还是后面放的。
对，它就知道这个东西就出来。
我觉得
就是还不是这里，是这个，就是你RI，就是你做那个编辑的时候，它所有在的 tree 这个 getting 你 actually 可以去对，你做那个
All right, we will continue on. So one of the things I did is I uploaded the code, so it's there, what I just typed, and I put in the notes, just a thing to check, look for the MATLAB coding for 1D CNNs. And again, these are ideas that you can use, leverage, if you will, for the last problem of the current homework, which is due on Monday. So it's coming up due on Monday, but I thought that might be useful. What I wanted to do now is talk about principal component analysis. And essentially, where it is useful, and essentially talk about some of the algorithms that people use, and also its relation to some of the algorithms that we've already talked about, because there is a strong relationship between the sorts of algorithms we're using, the gradient descent algorithms that we're using, in fact, for doing both adaptive filtering and neural network training, and the PCA methods that people use. Generally, the methods are iterative, although you can do calculations on covariance matrices. A lot of times the iterative methods become competitive, especially given the fact that some of these matrices are large and have kind of, what do I say? It's hard to compute the eigenvalues of a large matrix. And basically this is useful when the number of features in input patterns is large. And so the idea here is, you know, I have a system and I have something like my data. Remember, I've got my, you know, x1 up to some xn. But this L1 could be very large. It could be on the order of, you know, certainly 1,000 is not unreasonable. It might even be 10,000 or 100,000. You might say, okay, well, that's too large. I don't want to necessarily deal with those types of dimensions to be able to do the processing. Now, what this amounts to is we can perform a form of PCA, which basically will do a data reduction on this, so that what ends up happening is you still have your, if you will, you can think of them as x bar 1 to x bar n values, but now the dimension is much smaller. Okay, and so this is going to be, the size will be much less than L1. And so that will then make the possibility of running, you know, a classification algorithm or a training algorithm on it that much easier. Now, the issue, and one of the issues you have, is this process can, if you will, destroy spatial structure of the data. And that might be important. So the question is, this can be an issue in, say, CNNs, okay? That's true. I mean, it is the case. That generally is what you have to be concerned about. Now, there actually are ways to deal with this in terms of being able to make this PCA process, in some sense, convolutive. We're not going to necessarily talk about those in this class, but I want to point out that it is possible to kind of do those sorts of things. What I wanted, though, do though is introduce what this idea of PCA is, so that you have an idea of how you actually use it and what it's useful for. And so PCA, what is it? It is a dimension reduction tool, a dimensionality reduction tool. That is data dependent. This is the important thing. So you compute it based off of your measurements, okay? And the goal is to maintain as much of something as possible in the reduced variables. Okay. Now I know you're saying, you know, maintain as much what? I mean, you're saying what? You know, what's the thing that you're trying to maintain? Well, obviously, what you'd like to maintain, if there's some way to do it, would be information. I mean, if you're trying to do a processing which is information based, you want to retain information. And so we could talk about it in that context. But it turns out what we're really trying to do is, you know, think of information as second order. So really, we're trying to maintain energy. We're trying to essentially look for signal dimensions that are powerful. And the notation in this is going to change a little bit. So I'm actually, rather than referring these to x bars, I'm now going to start calling them y's. y1, if you will, y1 vector to yn. And so this is a little different, if you will. And again, it's to allow the notation from the handout that I've given you, this handout, to apply. This is essentially the notation that's being used in this textbook, what I've handed out for you. And the concept is, I have, if you will, the reduced data set. I have a set, move this back. I have the original data, which is again going to be x of n, n from 1 all the way to capital N. And then I have my reduced dimensionality data, and this would be y. I'll call this y of n. And the way we're going to compute y of n is with a linear transformation. So we're going to do a linear transformation. And we're going to go ahead and make this transformation a matrix W. So we have some W that we're going to compute here, times x. And again, now you can kind of see, oh yeah, this makes sense from the standpoint of this class, because we often do this. This here, the dimensionality of this is going to be essentially m rows and n columns. So these are the weights that I have. So I have a W11 to Wm, actually, we won't say small m, we'll say, I guess I'll have to choose some other notation. Let me try to choose something that at least resembles what he has. We'll do m out and m in. So we have m in and m out. So basically this allows me now to m out, m in, and it has a matrix that's this size. Okay. The important thing is that MO is less than MI. Otherwise, I'm not reducing. Right? So I have to have a matrix which is, the way I think of it is, I have a shorter vector is equal to a bigger matrix times a longer vector. Right? This is my Y, this is my W, this is my X. So I have to make sure that this, if you will, reduces the number of elements. Okay. In order to think about this, what I'm going to do is I'm going to think about a reconstructed data vector. And my reconstructed data vector I'm going to call x hat of n. X hat of n is going to also use W. So you're saying, well, how am I going to use it? Well, I'll go ahead and make W transpose times Y of n. So now what this does is it builds back up an X transpose by making it longer times this times that, right? And now the goal is to essentially design W such that some appropriate cost, some measure of error between x hat and x is minimized. This is my overall goal. And I can actually consider, what's a reasonable thing to do? I could do, say, sum of squared errors. And all this would be, and again, I could give this a k if I want to, j of k. This is just going to be 1 over n sum n from 1 to capital N. I'll say my x hat of n minus x of n. Euclidean length squared. So that's my idea. I'm going to try to reconstruct in this. Now, in this problem, as it turns out, W, actually, we'll say as fact, there are many, in fact, there's actually infinite W matrices that will achieve this. This minimization. So we actually need to think about sort of the class of matrices that I want. And this actually leads us to the idea of, well, we might want to constrain it. But the result that I've actually handed out to you and actually kind of posed this, you can actually rewrite this cost function. You can take this cost function, and it turns out what you have is, because you can push the n in, what you basically have is j of k being like an rxx minus a w times rxx times w transpose. And actually, I know you're saying, well, it doesn't exactly look like this. In fact, if you actually go through the math, you'll say, well, there's other W's that are associated with this. And there are, actually, maybe I'll say it this way. It's not equal to this. We have to do some simplifications, but the simplifications happen because we can think of this as the trace. This is the trace. So this is what we can, it turns out we can actually turn this cost function into this one, where Rxx is just 1 over n sum n from 1 to capital N of x of n, x of n transpose. So it is the, the correlation matrix that we're used to from the patterns. So this is the resulting equivalent cost function that we have if we essentially substitute it in. And again, use appropriate rules to be able to get there. And by doing so, by basically getting to this point, we can then figure out the following fact, which is that, that the solution of this minimization problem let me just, hold on a second. I just want to make sure. Yes. Is the following. Is W opt is equal to plus or minus E1 plus or minus E2 all the way up to plus or minus EMO, I guess it is, the number of outputs, times T, where this is any square orthogonal matrix, MO by MO in this case, matrix. And these are the first MO eigenvalues of basically Rxx. So it's an eigenvalue decomposition. If I know the first MO eigenvalues, which is again, MO is less than MI, then it turns out I can take those eigenvalues, or not eigenvalues, eigenvectors, apologize, eigenvectors. I need to find the eigenvalues generally to find the eigenvectors as well. But these are the first MO eigenvectors of Rxx, and then this is any rotation of that. And again, these, they could be plus or minus. I don't have to have any particular direction associated with them either. And this is under the constraint that W transpose is identity. And this means that W has orthogonal. Actually, let me just, oh, you know what? I messed up there. This should be transposed. Okay, now it's the right size. I need to have something that's sized like that. So basically, W has orthogonal rows, right? The columns here are orthogonal with the transpose. The rows are orthogonal. Now, if you think about this, this actually kind of makes sense that we would want to build in this constraint. This minimization problem is kind of an ugly minimization problem because it's second order for one. But clearly there's some degrees of freedom that we don't necessarily want to deal with. For example, we don't want to have to deal with is W getting large or small. By constraining the resulting solution to have basically orthonormal rows, then we're able to basically build a solution such that this constraint, it reduces our search space. Maybe that's the best way to say it. It reduces the types of matrices that we have to look across. And it allows us to consider algorithms which would maintain this constraint, which actually is sort of the interesting part of this particular field. And, under this solution, then it turns out that this J of K, when you minimize it for all W, basically it's equal to the sum of I from MO plus 1 to MI of lambda I. These are kind of the smallest MI minus MO eigenvalues. So the actual cost function is reduced down to kind of the energy. And so another way to think of this is the energy in the null space of this, W matrix. So if we think about these vectors, they'll basically, and this has to do with the concept of a subspace. If I have a W, say my W transpose has some number of eigenvalues, E1, or eigenvectors, EMO, then these basically are a coordinate system for a MO dimensional space. Right? But they have their coordinate system for MO dimensional space because they give you axes. But you have fewer dimensions, you have fewer axes than you do dimensions because obviously, this dimension here is MI. So, the classic way to think of it is, well, if I have two orthogonal vectors and I move along those two orthogonal vectors, any linear combination, that gets me to a 2D plane. But of course, these could live in a 3D space, right? These could have, they could have life in a 3D space. So this represents what's called the subspace reached by the rows of W, right? It's the place that you can go by basically taking linear combinations of all these different vectors. And then, there is space that you can't reach, which is this null space, which again is something that, you're not going to be concerned about, at least from the standpoint of the optimization problem, because, those are the dimensions that have the minimum power in them. So I'm not going to be too concerned about trying to reach those. Now, why is it that we end up getting into a subspace? Well, the way to think of it is, if my data kind of represents a point cloud, so I have data that's kind of in a three-dimensional cloud, well, most of the variability is in the direction of the plane, right? And there's very little variability, so there's little variability. There's little variability in the direction perpendicular to this plane. That's the way to think of it. So we're kind of, if we think about all the points that would be projected down to this plane, then that kind of captures most of the energy that we have, and there's little variability away. So the idea here is my finding an optimum W is basically equivalent to orienting a MO dimensional subspace onto my data and kind of looking for the plane that's going to somehow slice through my data and capture most of the variability. And then when you do that, the actual values that you would get in the plane are actually the y's. So the way to think of it is, I have this point cloud that kind of lives here. If I get all the values that actually, are the closest points to all my data, then these are actually the y values. So these are the, if you will, the yn entries, are all the values that would live in the plane that are kind of my approximation to the point cloud. So the basic goal of this is to try to build a set of axes that will then yield y's that still grab most of the variability, and then use those y's in place of the x's wherever I was planning to. For example, if I'm going to do a pattern recognition problem, I would use that instead. So that's the basic concept. That's the reason why, or that's how this problem is set up, and that's the reason why power is important from the standpoint of cost function, because we're trying to measure the variability associated with this data and characterize it so that, again, we can get these points and use the y values in place of the point cloud values so that we can reduce the dimensions. And again, that's going to reduce all the processing after it. Now, the question is, what are the mechanisms to do this? So the question is how to do this. Well, really what we want to do is we want to solve problems of the following. Solve problems of the following sort. I might want to minimize across all W some cost function J such that W transpose equals identity. I want to do that. I want to have a constrained optimization. It turns out that actually I also might want to consider the maximization of a cost. We can either have it be formulated as a minimization problem. A minimization problem kind of makes sense here because if you think about it as an approximation problem, it's find a transformation such that, this x hat is basically W transpose WX. Find the transformation so that this guy is close to that. But you can kind of see that if I look at the cost function, this is actually equal to W, this turns out to be equal to 1 over n sum n from 1 to capital N of yn transpose. So what I might think about is, maximizing the output power. So in this context, I might think of this as an output power, or really energy cost for maximization. Here, I'm going to think of this as a reconstruction cost. Reconstruction error cost, right? But I need to solve these sorts of problems, okay? So the question is, what are mechanisms for doing this? Well, I want to talk about probably the two most famous methods for doing this. And I would say, methods that use RXX directly. So we could, one way to solve this problem, since we have the form of the solution, one way to solve this problem is to essentially, form RXX and calculate the eigenvalue decomposition. And then after I've done this, and then use, at this point I would use, basically W would be, E1 transpose to EMO transpose, right? I would just take those vectors, the first MO eigenvectors. So if you have the ability to actually form RXX and then do this calculation, then you could just take the eigenvectors and be done. And that's typically, if you have a data set where you can do this calculation, that's what you would do. The issue here is this could be costly if basically MI is large. That's one thing. The other issue you have, and I want to bring up this issue, you might not have eig function handy, right? I mean, you're trying to, to formulate this. If you don't have LinPack and IcePack coded up for your particular problem, or maybe you're trying to do this in an environment where it's a little tricky, like you're doing it on a processor where you're trying to manage resources and so on, you don't necessarily want to bring in, a very complicated set of functions to try to make that happen. So these are some issues that can come up when you're doing this. So it's good to have iterative methods. Iterative method for basically MO equal to 1. This is called the power method. The power method is a very, very simple algorithm. The basic idea here is now my W is just a single vector. What I do is I set W to be some initial, actually mi dimensional vector. And I do for I equal to 1, 2, and so on. I basically say W tilde gets Rxx times W. And I guess I'll give this an iteration since we have been using iterations. Wk plus 1 gets Rxx times Wk. So I set W0. And I say I. We'll go ahead and say K. K from 0, 1. We do this, and then we say Wk is equal to W tilde. Actually, I guess K plus 1. K plus 1 gets W tilde K plus 1 divided by the length of W tilde K plus 1. So this is the algorithm. And this is Euclidean length. So this is the resulting algorithm that you would use for one vector. And we basically, you end this at some point when you decide that this particular vector is close enough. It's not changing very much, for example. What you can show that the speed of convergence of this depends on the ratio of lambda 2 over lambda 1, where this is the next largest eigenvalue. Right, and this obviously is the largest eigenvalue. So if your second eigenvalue is much smaller than the first, then this algorithm converges very fast. If the second eigenvalue is close to the first, then, say this is 0.99, it may take a while for 0.99 to an nth power to actually become small and get error terms that go down. So that's what I mean by speed of convergence. Basically, smaller is better. Smaller is faster for this. So this particular approach, is useful. And by the way, it's a useful technique because it doesn't require any, eigendecomposition. You can just apply this iteratively and get a good estimate of the eigenvector. And then, of course, once you've got that, you would then use W. You would use Y of n to be basically W transpose of final times x. Now, in this case, you've reduced it down to one value per pattern. So this is probably too aggressive for us, right? We're not going to take our data and turn it down to a scalar. So we need the multi-dimensional equivalent of this. So you can think of this as a multi-dimensional power method. What is the multi-dimensional power method that is the equivalent of this? Well, there's a way to describe it. It's actually called orthogonal iterations. And the method goes like this. Basically, what you do is you set up a P matrix. This P, so here you're going to initialize your W. You would initialize some sort of W naught, which again is going to be our matrix, which is like that size, with some entries in it. Okay? And then what you do is you say Q, so we do for K equal to 0, 1, and so on. You would say Q of K equals W of K transpose. You would then find a P of K to be Rxx times Q of K. And then you would find a set of matrices, which are, this is going to be called Q, and I'm going to call this R tilde. I have to call this something else here, Q k plus 1, R tilde k plus 1 equals P k, where this Q, this is the so-called QR decomposition. So you would do a QR decomposition on this P, and recognize that this P is now, since this Q, this Q is like this, then the P is going to be also that dimension. Then the QR decomposition is going to be an orthogonal matrix. This is the Q k plus 1. This is this orthogonal matrix times R, where this R tilde is an upper triangular matrix. That's how it's done. So this has orthogonal columns. This is an upper triangular matrix, and you're finding that to be equal to this. And then you essentially stick this back to here, right? So actually, we don't need to reassign the W. I guess you could say, though, that we could call W k plus 1 equaling Q k plus 1 transpose, right? That would finish out the iteration. But basically, you iterate these two in the middle, and then when you're done, you just take the transpose of the Q and you get your W. So that will essentially produce the multidimensional equivalent of this. And this, basically, what you can do is you can show that that the convergence speed of this depends on the ratio of lambda MO plus 1 over lambda MO. So it's kind of the speed of convergence now depends upon kind of the ratio of eigenvalues of the I should say of the mth dimension, right? No, eigenvalues near the MO dimension limit. So the concept is basically, we've moved the problem from the first and second dimension, which is up here, to now kind of the dimensions where, well, we don't care about the first or second dimension, we care about the second and the third if we're talking about a projection from 3 down to 2. So we care about the ratio of those powers as opposed to the ratios of the powers in the signal space. So this is a technique. Now, granted, it does require a QR decomposition, so you do have to have that available to you. But this is actually the starting point for our various approximations. That's why it's important to us. All right, we'll go ahead and pause here, and we will continue our discussion and also show you how this builds up into independent component analysis, which is another mechanism for reducing dimensionality. All right, so we'll stop there. Remember, homework's due on Monday, and we'll see you then. Yes. Sure.
It's 3x3 and stride is 2, but by each row it should be considered 2 or 3?
Well, the thing is, you're doing max pooling, and then you're moving over only 2. So you may not reach all the data points in this because I don't want you to zero pad.
So, for example, the last
maybe the last column doesn't even get